Hello folks, this is a concept inventory on chapter 5, thermochemistry. This is the one we did in class. A lot of you missed this for the track meet, so let's go. On the following, which is a state function, we know heat, well, that's Q, and that's equal to mc delta T. We have delta H, and that's our change in enthalpy from the final minus the enthalpy of the initial. We have work. Work is equal, force times distance, or pressure times volume, and Q is the same. And we have to figure out which one is state function. Well, we know that this one is delta H. Delta H indicates what is not the path dependent. Well, what does that mean? That means that a delta is there, so it is a state function, and delta is always going to be our final minus the initial. And that is our answer, B. A blank delta H corresponds to a blank process. Negative exothermic, right here, B. A negative H corresponds to an exothermic process. A blank corresponds to a blank process. Negative endothermic, 0, 0, positive exo, or positive endo. If it's positive, delta H, it will be an endothermic process. Last but not least, enthalpy change for the reaction is negative 483.6. So if we compare these two reactions, this delta H is equal to negative 483.6 kilojoules. Well, the difference between these two reactions is that it's twice enough, or twice the amount. So the delta H for this reaction is going to be 2 times our number, negative 483.6 kilojoules. So we're going to double the enthalpy as well, and we can do that because it's a state function. Okay, now let's get to the fun ones. The value of delta H naught at the reaction is negative 72 kilojoules, so it's exothermic. So add that in here. Blank kilojoules of heat are released. All right, that means it's leaving the reaction when 80.9 grams of HBr is formed in this reaction. Okay, so what do we do here? Well, where do we start? We always start with what's given. So this is what's given. So we start here. So 80.9 grams of HBr. And we got to convert that into moles. So what units? The same unit that's here is going to be down here, grams of HBr. And there's 81 grams in 1 mole of HBr. Now that I'm converting my grams into moles, we can use the enthalpy of 2 moles of HBr divided by negative 72 kilojoules. Now, where did that number come from? Well, if I look back at my balanced equation, I have 2 moles here and my enthalpy here. So if I combine these two, I will get negative 72 divided by 2 moles. And that's where this comes from. And this is what we call our energy ratio, or energy per mole ratio. So I pop all those into a calculator, and I get about negative 36 kilojoules per mole. I'm sorry, just kilojoules. What am I doing? Cool. So there's our stoichiometric equation. Just to review, we start with what's given. Here, we converted to moles with our molar ratio. Here, then we multiply that by our enthalpy here. Excellent. Let's go to the next one. So our enthalpy for reaction is negative 126 kilojoules, and our starting material is 2 moles of NaOH, so we can start here. So if we have, so first off, we start here with our 2 moles of NaOH, and then we multiply by our enthalpy energy per mole ratio. We know there's 126 kilojoules per 4 moles of NaOH. Multiply the two together, and we get, let's see, and we get negative 63 kilojoules of energy produced. Our next reaction, C3OH, yields CO plus 2H2 with the enthalpy change of plus 128 kilojoules. And we know that there's 5.10 grams of H2 given. That's what's produced, that's what's formed. Let's start with that. So first we convert 5.1 grams of H2 into moles of H2 by dividing by the molar ratio, 2 grams per mole. Then we multiply by the energy per mole ratio of 128 kilojoules by 2 moles of H2O. Now we know that there's 2 moles of H2 because of our molar coefficient in our balanced equation. That yields about 163 kilojoules of energy consumed in this reaction. And just a footnote, if this number is positive, well, this one should also be positive, and vice versa. And that's it. Good luck, and I'll see you in class.